front? Yeah, okay. Is there a volume knob?
I don't, someplace I can try to adjust it. So you're going to hear
hardware hackers is, I know, but that's too much work.
You keep them lined up and you got it. Right, this is started. So, okay. Actually, later on, copy everything that's completed, or move everything that's completed to that. Okay. Joe, we're actually recording the talk right now. So,
what's that?
I'll see if I can find the audio box.
Okay. Well, I'm ready whenever you are, so.
Sure. I have no idea. What the hell is it?
No volume knobs. That's fine.
I'm sorry, guys.
That's good.
I know what we have right here.
I'll just speak softer.
Sorry.
Cool. Okay. Are you guys good? Are you recording?
We're recording.
Good. Okay. Thank you guys for coming. My name is Joe Grand, and we're here for some Jtagulator action. Jtagulator is a tool that I just put together over the past few months, and I'm going to go through some of the background of it, how it works, and what it's about. And the tool really is to help hardware hackers get into software and identify on-chip debug interfaces, things like JTAG, on a target circuit board. So here we go. How many of you guys have been involved in any sort of hardware hacking or kind of tinkering with electronics? Okay. About half, maybe a little more. How many of you guys have messed around with debug interfaces and various stuff? Okay, like a quarter of those. Mostly like drives and serial ports and stuff. Yeah, okay. Awesome. Great. So, sorry you guys can't actually read the slides. So yeah, debug interfaces on circuit boards are really one of these well-known attack vectors. So if you're into hardware hacking, one of the first things you do when you open up a board, you look for the main components, and then you look for any sort of interfaces that you might be able to connect to and possibly attack or get some sort of information about the system from. So that's something that this tool is really going to help with, is trying to find those interfaces and tell you what they actually are. The one thing that we can take advantage of as hackers is that these interfaces, even though some vendors know that people might use those to try to break products, it's something that they need for their manufacturing. It would just prevent legitimate engineers and legitimate manufacturers from testing products, from programming products after, during the production cycle. So it's sort of one of these things that they need, and we can take advantage of that, and because we know that they're there. But the big problem is sometimes identifying these interfaces, if you don't have the hardware hacking skills or you don't have the resources to do it, sometimes it's really easy, and I'll show you some examples of that. Sometimes it's more difficult. So I want to come up with a way to make it easy for people that aren't traditional hardware guys to get involved in hardware hacking and sort of, do some of the hard work for them so they can actually start doing some of the fun stuff. There's a few projects that sort of inspired me to do this. One of them, the first one was Hunz's JTAG Finder, which he gave a talk about in 2006, which was, I believe, like on an Atmel evaluation board or something. It basically proved the concept that, yes, you could do this kind of JTAG enumeration, like brute forcing of a bunch of unknown test points and have it try lots of different permutations until it actually comes back with the right set. So he proved that concept and kind of showed it was possible, but the tool was very rough. It wasn't like a traditional type of tool. So after I saw that, I was like, that's pretty cool. So I did some research online and came about the JTAG enum and RS-232 enum projects that were done by a guy named Dead Hacker. And he had basically taken Hunz's work and refined it a little bit into an Arduino platform. So slightly more usable, but I thought it was kind of missing some key features, mainly input protection, adjustable level voltage levels for the target circuit board, and just stuff that I would personally want to use. And since I'm not really an Arduino person, I was like, okay, I'm going to try to make something that I would want to use and that I would be able to recommend to people. And then the final piece of inspiration was Cyber Fast Track, very cool DARPA program that I know a lot of you guys have probably taken advantage of to work on projects. Pretty much everyone I know had been doing a CFT project, and I was like, well, I want to do one too. What am I going to do? I haven't done like a security project in a while. So I submitted, I did all this research about JTAG and how I could enumerate these different interfaces and how I would design it. Wrote a whole proposal about it, submitted it to Cyber Fast Track, and got rejected for having too much engineering. So it's sort of like, DARPA projects are usually research focused, but I had done too much research to write the proposal, and I knew exactly what I was going to do, so it was like they didn't want it. So at that point, I'm like, damn, I'm going to do it anyway. I'm going to show those guys, I'm going to show Mudge that I can design this thing. So that was like an inspiration for me, sort of a kick in the ass to do it anyway. And there's lots of wire art out there. Travis Goodspeed has the Good Fed and a bunch of presentations about the Good Fed, which is sort of a general purpose. Started as like a MSP430 JTAG programmer, but that also has some kind of open source JTAG interface capabilities, not enumeration but interface. So there's some work that he had done. There's some other work out there as well, but nothing as like a, again, like a full-on platform. So when you're looking at hardware devices, sometimes you can find external interfaces, so things that are accessible to the outside world that you don't even have to open up the device to get to. So external things like connections hidden under stickers, so like the RSA Secure ID token, or behind like a plastic plug. On the right, I guess I don't know, this side, that little 4-pin weird thing is from a Jawbone Up wristband, where you have the button on the end of the Jawbone Up. And I'm pretty sure that those 4 pins around it are the debugger programming interface. Because usually the way the manufacturing process would work is someone's making a product, you usually assemble the product, program it at the end, maybe do your testing and then program it as the final thing. So if the firmware changes, you don't want to have your part already programmed and have no capability to program it before it goes out the door. So that's a possibility. You pop the cap off and now you potentially have access to reprogram the device without having to open it at all. So that's external interfaces. Those are usually pretty easy to find, and when you do, it's like, okay, the fact that they're brought out to the outside world tells you that it's probably something you should be looking at. But you still might not know the pinout, right? So that's the challenge. Internal interfaces are a little harder to identify, but not always. Sometimes it's really easy. So it might be in the form of like test points or unpopulated pads. So the picture on the left is from a cordless phone that you pull the board off, and there's, I don't know if you can see it on there, but there's 4 giant circles, like right in the center. Those are very obvious test points of some sort. And sometimes you encounter boards that even have silkscreen markings on them. So on that board, it actually says, above each test point, it says feedback, ground, I2C clock, and I2C data. So right away, it's like, okay, we know that's an I2C interface, that's an inter-chip communication interface with a clock and data line, that's what they use, and then ground and power. So that, all the work was done for us. Now we can connect up our digital oscilloscope, our logic analyzer, our bus pirate, or whatever, and then go to town doing the attack. Other times, this picture, the other picture is a BlackBerry device, and you can see there's like, what's circled there is like a big clumping of test points, right? There's 7 test points that are very obviously together compared to other test points around the board. Like there's that row of smaller test points and there's some all over the board. But those 7 that are right there, it's like, okay, that's probably something useful, right? They put it there for a reason in that grouping. And it also turns out that this particular device, if you took the label off of the back of the BlackBerry, you can actually access those pins externally. So again, it's another one of those like very obvious things. But you don't know the pinout. Sometimes you do encounter boards that make it much easier for you, just like the cordless phone, but in this case, here's a Windows CE based platform that was from the ATM that Barnaby Jack had hacked a few years ago, where he opened up this board, had physical access to the device, Windows CE, and he used a common industry standard pinout for JTAG. So all he had to do was go and buy an off-the-shelf JTAG interface, plug it right in there, connect up to his computer, use the legitimate design tools, and start hacking the ATM. So that was a really nice thing that they did for that ATM. The other side is from the Xbox. That's just another example of silkscreen markings that engineers put on boards to make it easier for them, to make it easier for manufacturers, but it's something that we can take advantage of. Anything that's there on the board for an engineer, we can use. So in this case, it's a low pin count debug board, and that's a defined pinout as well. So sometimes you get lucky when you open up a board and you know exactly what it's going to be. Other times you might have an idea, but you're not sure if it's an interface. So you can sort of use PCB design heuristics and look at the board and say, okay, I see like an unpopulated connector on the board. I see a bunch of traces all going together down the side of the board. Chances are that's going to be some sort of interface. And buses usually will travel together. Engineers who lay out boards will make all similar signals travel together down to where they need to go. You're not going to normally see them go all over the board if they're a common bus. So in that case, you can say, okay, that's probably an interface that maybe we want to try to figure out. On the other picture, that was from I think that was from a wireless access point I was looking at. maybe the D-Link, like the DWL 900. That one didn't have that actual 2-row header on there. I soldered that on. But if you imagine that that connector isn't there, what I have circled is like a resistor array. And those are pull-up and pull-down resistors that sometimes are also used for buses or interfaces or on-chip debug interfaces. So you can see that resistor array and say, okay, well, there's a resistor array right next to that unpopulated header. That's probably something I should be looking at. And those would be pull-ups and pull-downs to set the idle kind of static state of those bus lines. So we can sort of get some clues. Sometimes things get really hard though. Or you encounter a board like this, where the JTAG interface is actually on the pads of unpopulated components. I don't know if the vendor was trying to be sneaky in this case, or if they actually would put resistors there, but I'm guessing that they were trying to be sneaky. So instead of having a very obvious interface that a hacker could clip right onto and use their off-the-shelf tools, they had to actually search for them. And this is security through obscurity, right? Security through obscurity doesn't work. As soon as somebody finds that interface, there's no more security. So now somebody can connect directly to it. But if you don't know, that's hard. I mean, there's unpopulated parts all over boards. So it's like, how do you figure out what those are? And that's where the Jtagulator comes into play. So prior to some of this work, you had to manually determine pin function, and sometimes you still need to do that up to a point, just to maybe give you some general sense of which pins you want to connect to. But usually what you do is you identify your test points. Maybe you use a multimeter in a continuity mode to trace out connections. So say you do have access to the microcontroller, you have access to the pins on the microcontroller, and you identify your connector, you can say, okay, what does pin 1 of the connector connect to on the microcontroller? And sort of probe around and see what's going on. It takes a lot of work, and it takes a lot of time. You can also then, once you've identified connections, use the oscilloscope, take a look and see if you see any clock signals, or see if you see anything obvious that maybe gives you a clue that it's one type of interface. Maybe like JTAG has a default pin, like one of the pins is default pulled high, and one of the other ones is default pulled low. So if you see that, you're like, okay, maybe that's JTAG, or maybe it's SPI, or maybe it's I2C, or maybe it's something else. So you can sort of get clues, but not really. And it gets even worse. If you have a part with a VGA component on it, a ball grid array component, where all of the connections are underneath the chip, which is very common these days for pretty much any mobile phone, any consumer device with any sort of integration at all, you can't probe pins anymore, so you can't really manually trace stuff out anymore. It gets to be a real pain in the ass. In this case, you have to use X-ray, so you can see through the board and maybe try to trace out where connections go, or you have to physically remove the VGA part from the board so you can trace stuff out. If you don't have the skills to do this, it's pretty much an impossible task, right? I mean, it's a sort of, if you've never been into it before, thinking about removing a ball grid array component and tracing out 384 connections where they go is sort of a hard thing. And if you only have one unit, right? What if you only have one unit and you don't want to risk taking it apart? So a little bit risky. And this stuff can get messy. So we try to avoid all of that stuff. I'm going to talk quickly about two of the debug interfaces that Jtagulator currently supports, JTAG and UART. And the hope is to add all of the design files, everything is open source for this thing, so you can build your own if you want. And the hope is to add more protocols, more support for more interfaces, because every vendor also has their own vendor-specific type of debug interface. JTAG is an industry standard. But then, like, Freescale has their background debug mode, Microchip has their ICSP interface, and Atmel has theirs. So it'd be cool to add functionality for all of that. Even though for a lot of those embedded systems, a lot of those kind of lower-end parts, I guess, it would be pretty easy to manually trace stuff out. But I think it'd be cool to add the functionality there. So JTAG is an industry standard interface, IEEE 1149.1 if you want to read the actual specification about it. It's really boring, and I think it's almost like they intentionally made it hard to understand, just so the engineers that wrote it look really smart. Because it's not a very complicated specification, but it's just super boring to read. And once I read through it, at first I was a little intimidated because I see all these drawings and graphs and stuff, and I'm like, this looks really hard for an interface. And then once I kind of digested it all, it's like, okay, it's not really that bad. So I'll do my best to sort of explain it. The spec really defines like a low-level interaction between the chip and the outside world. And the original intent of JTAG was to test if a highly integrated part, like a multi-pin part, was properly soldered down to the board. So say you have a part with 300 pins or something like that, or 300 balls, and you can't see them all. If you had this way to test the solder connection of every single one by controlling each individual pin and then comparing that to the value of a test point that you're measuring, that's sort of a good thing to test the solderability. This is sort of like, before the ubiquity of X-ray. So that's how it sort of started. And really it defines this, JTAG is really like a low-level finite state machine. And really like a little tiny CPU with a few different opcodes, and you can choose different registers. You can load instructions into an instruction register, and then you can select which data register you want to interact with. And it sort of just ships those registers in, and it will ship data out as you need it. But what's really cool about JTAG, and what's different with JTAG compared to some of the vendor-specific interfaces, is that you get this direct interface to hardware and can do some really insane stuff. First, because it was designed for what was called the boundary scan test, to test each individual pin, you can control every single pin, either drive signals out on every single pin or read data in on pins that are inputs or outputs. So that's pretty cool. And because you can do that, you can now hijack other components that are connected to that device on the bus. So say if you're accessing a CPU through JTAG, and that CPU is connected to a piece of flash memory, if you can twiddle those bits of the CPU, now you can communicate with the flash memory and try to suck data back out. Sometimes vendors will build higher level functionality on top of that, so things like programming interfaces that will let you program internal flash of a device or read internal RAM of a device. It gives you this full control, so now it's not really just a test interface as it was designed, but it's a full programming interface, full debug interface a lot of times. So it's a really, really cool interface. And this is the reason why vendors are normally not going to get rid of it, right? It's just too useful for them to get rid of it. What's also neat about JTAG is multiple devices can be chained together, so you don't have to have an individual interface for every single part of the board. So assume like a highly integrated device these days, like a mobile phone, might have a CPU, baseband, flash, maybe a few different flash chips on there for different storage areas, whatever it is. You can have one single JTAG interface that chains all of those together, and you can communicate to all of them. Because JTAG is basically like a giant shift register. And you can set different parts into a bypass state, so if you don't want to talk to chip number 1 in the chain, but you want to talk to chip number 2 and 3, you set the first one into bypass, and that sort of skips over itself and pushes the data out to the other ones. So it's sort of cool. I have a picture of that I'll show you later. And really, the thing to keep in mind is we don't really need to care how JTAG operates. All we want to know is, we need to know the few things that will enable us to determine the interface, and then at that point, once you know the interface, you can just use any off-the-shelf JTAG hardware, whether it's like some OpenOCD thing or I'll give you some vendor lists. Usually what I do is, like, if I'm hacking a board, say it's that has a Broadcom chipset, and I find the JTAG interface, I'll try to contact Broadcom or see what people are using to communicate with Broadcom devices, and try to use like what the vendor recommends or what they would recommend to a legitimate engineer to use to work with their devices. It just sort of removes some of the unknowns as opposed to using just like a general purpose, third-party off-the-shelf JTAG interface that may or may not work. But whatever it is, we don't really care. As long as we find the pin out, there's plenty of other really, really good tools that will do the rest of the work for us. So JTAG is a synchronous interface, which means it requires an external clock. It's a little hard to see up there, but there's 4 required pins where you have your data in, that goes data to the target device, and you have data out, that's data from the target device. Mode select is going to let you select the different mode, the different state of the tap of the JTAG state machine, and then you have your clock. There's also a reset pin that some devices use that's for an asynchronous reset, which means you can reset the tap back to a known state by pulling that pin low. But you can also reset the tap back to a known state by clocking some number of cycles with TMS high. So you can sort of skip through the finite state machine back to the beginning. So we don't really need that reset pin at all, because we want to know that we're resetting the device, but we don't need that extra pin. So the tap, again, is shift registers. Our instruction register has to be more than 2 bits. That's just the definition from JTAG. And then the data register is you have your bypass register, which if we want to skip that part, we would load in that bypass register. All that does is clock the data from TDI out to TDO. It just passes it right through and it's just delayed by the one clock cycle of going through that 1-bit register. Boundary scan will depend on the number of pins of the actual device, because that's what's going to let us control each individual pin. And then the device ID is another way that we use to try and determine the interface. And device ID is a 32-bit register. It's optional per the JTAG spec, but pretty much everybody uses it. And it's a device identifier that will identify the manufacturer, the architecture type, and some other stuff. And there's a whole description. The device IDs are issued by JTAG, and I have a link in the slide that you can actually see. So once you get a device ID, even if you don't know what the part is, if you get the device ID, now you can go and work backwards and try to see what that device ID is, look up the vendor, and try to figure out exactly what that part is if you don't know it already. Here's a kind of high-level view of what JTAG would look like inside of a part. All of the important stuff's at the bottom, and then you can see the individual I/O pins for the boundary scan register, and the BSC is the boundary scan cell. So there's an individual piece of digital logic that lets you control each of those I/O pins. Here's another view of just the state machine itself. And this is what I looked at and I'm like, this just seems unnecessarily complicated, but it's actually not too bad. And the state transitions are based on the value of TMS and then the rising edge of the clock. So we can just move our way through the state machine. Say we want to load in a new instruction into the instruction register. We shift over to the capture IR state, shift in our data, and then latch it in to the register. So it actually isn't that difficult. And then if we want to shift data out, we would go to the shift data register and shift data out of that. Sometimes some interfaces do try to implement some sort of security protection. It's not as common as you would expect, and I think we'll see more and more of it. As far as some companies try to just be sneaky and disable the interface in some way once the device is ready for release. So they use JTAG for development, for programming, for manufacturing, cut traces or remove jumpers or something just to make the interface not work. So you might need to, if you see that you think you have an interface and there's connections missing, it's maybe they're trying to be sneaky and obfuscate the interface. Some devices do have password protection, that you have to send some sort of password into some register in the tab, some custom addition that a vendor has put in there. One example that somebody had told me once was they had a flash device, or they had a microcontroller with internal flash, that after some number of attempts, of invalid password attempts, the flash would be erased. But there was no kind of volatile, or there was no non-volatile flag, right? So you could try it n-1 times, and if you didn't get it, you reset the device, and it would reset the counter, and you could sort of brute force it that way. But all the password implementation, there's nothing standard. So anybody that does it, it's their own custom thing, which probably means that there's going to be problems with it. Sometimes too, if there is password protection, you might still be able to access the bypass mode. So that way they stay somewhat JTAG compliant. So we'll still be able to identify the interface, we might not be able to use it though. So here's a list of some of the hardware tools I mentioned once you find that interface. There's some common ones like the RIF box is used a lot, HJTAG, those you have to pay money for. There's open source one, you can build a parallel port version. For some of those, the RIF box has their own tools, HJTAG has their own tools. Sometimes hardware tools that are recommended by vendors have support within the vendor's development environment. So if you're looking at some sort of ARM processor, say a Freescale Kinetis part or something like that, you could use the Freescale Code Warrior tools along with their JTAG hardware interface that they recommend to now go through and extract memory and look at stuff. Otherwise, if you're using one of these kind of third-party ones, you might need to use their software or some other software like OpenOCD or UART JTAG. So there's lots of resources out there. So that's JTAG in a nutshell. UART, we're all familiar with UARTs. DB9 connections, serial port connections, asynchronous serial data is all it is. Where no external clock is needed, so normally you would find you'd have a TX and an RX line. And the timing would be built into the signal, which would be the baud rate. What we're mostly looking for, back in the day, we'd also have to use hardware, handshaking, and other control signals and stuff, but most of the time for modern implementations on systems, and normally we see these for debug outputs, or consoles or root shells. I'll give you a demo of that. You just use TX and RX, transmit and receive. So all we really are going to need to do is send data on TX and see what comes back on RX, and if it is something that looks like data, we'll kind of save that in our list. Here's a screenshot of what asynchronous data looks like, where the data is going to vary based on timing, and the baud rate can be calculated by what's called the bit width, which is the smallest kind of transition time of a transfer. So this is a screenshot from my oscilloscope just showing I sent some data from, I don't remember what I sent it from, but I captured it with the scope. And you can sort of see, I measured the bit width around 8.7 microseconds, which ends up being 1 over 8.7 is 114.9 kilobits per second. And the closest standard baud rate to that would be 115.2. So that's the baud rate, 115.2. And my scope actually has digital decoding functionality, so I can actually set the baud rate and make sure that's right. So assuming you don't have something like this, it would be a nice, it'd be nice to try to figure out where the interfaces are. All right, so jumping ahead to the actual hardware design of the Jtagulator. I want to make it open source, obviously, for this community. It seems sort of silly to make a piece of hardware for the hacking community where people can't modify it and build it their own and learn from it and do what they want with it. So that had to be that way. I like to do things with products as have like a simple command-based interface. So that's what the Jtagulator does. It's a command-based interface you connect to, it shows up as a virtual COM port, use whatever terminal program you want, and just type commands and get information back. It has proper input protection, which I'll talk about, so you don't fry other circuits, and so you don't fry the Jtagulator by accident. Adjustable target voltage to make sure you're communicating at the right levels that the target system is actually expecting. All off-the-shelf components, you can get them all from DigiKey or Mouser or your favorite electronics store. And if you want, you can actually hand solder it. I don't know if you can actually I'll show you actually a picture on the next slide. There's a lot of surface mount parts and a lot of fine pitch parts. You can definitely do it. It would be good. It would be sort of like an advanced learn to solder platform. So the block diagram, I'll go through some of this stuff in a little more detail, but basically we have a parallax propeller microcontroller in the center. This is a really cool, like 8-core processor. And Parallax is a very, very cool company that makes all sorts of educational electronics and hobbyist stuff. I've worked with them for a lot, so I figured it'd be cool to use their part. Super hackable. Actually, the Parallax, the propeller is used on like on the DEF CON badge, DEF CON 20, and for all sorts of other project stuff. It's a very, very cool hackable platform. So we have an FTDI serial USB interface that's going to power the Jtagulator and also serve as our command interface, and also serve as a way to change firmware on the propeller. So it's a multi-use interface, which is kind of cool. For our adjustable target voltage, we have a D to A set up with an op amp. We have our level translators going out to the input protection circuitry, and it's some power supply stuff. Here's a view of the board. I figured what better, my joke isn't going to work because the board looks blue on there. The board is not blue, it's pink. And what better way than to have an awesome name like Jtagulator with a pink circuit board. So hot pink is what it is. Also, it's easy to identify, like when it's on your desk and you have piles of crap everywhere, you know it's there. But blue doesn't actually look too bad either, but pink is better. So you can sort of see if we start from the USB connector over here, that's where the FTDI stuff is. We have a status light that will turn red or green depending on if it's in the Jtagulator. If it's Jtagulating or not, it will turn red if it is. The propeller is there, the op amp is down at the bottom. Our level translation, which is going to convert the 3.3 level signals from the propeller to the adjustable target voltage, which I'll show you, which is I think 1.2 to 3.3 volts. Input protection are going to be diodes and resistors, and then we have our target interface on the left. So we have 24 channels that we can hook up to. 24 test points is a lot of test points, and you'll see that that's a lot of permutations. A lot of possibilities. So you can either use the screw terminals on the top or the 2x5 row headers down at the bottom that are also Bus Pirate probe compatible. So if you have a Bus Pirate, you can clip on the probes, and then you have your little test leads, alligator clips you can clip on the stuff. It just makes it easier. So the propeller itself, it is this 8-core system. The chip was designed from the ground up by a guy named Chip Gracie, who helps run Parallax, who started Parallax, an amazing hacker and engineer, and he wanted something that would be kind of fun for people to mess with. And it definitely is. There's lots of code out there, lots of projects going on, lots of resources. So you can either write in Spin, which is sort of this high-level Pascal type of language, or assembly, or now C. if you want. Spin's like Python, yeah. Yeah, I guess it sort of is like Python. A little bit of a learning curve to learn Spin if you haven't worked with I guess it's almost like a much higher level language than anybody that's worked with electronics normally is used to. But it's pretty cool, and it's a very powerful part. Normally it's running at 80 megahertz. And it has some individual memory for each cog. And you can think of a cog as like an individual core, and everything is sort of running in time slice. You can share I/O pins and stuff. But there's just lots of, you can build on the Jtagulator and have tons of functionality because there's basically, like I'm hardly using any resources, which is cool. Standard development is done with what's called the Propeller tool and the Parallax serial terminal. There is something for OS X that's called Brad Spin tool, which is a third-party tool. And then they are working on a multi-platform Spin tool as well. There is a multi-platform C environment already, but I used Spin for the Jtagulator. So the USB interface I talked about, you can use it for programming, for powering the device, and then as our command interface. It's just a very simple implementation of the FT232 and a power distribution switch. Because to be USB compliant, you can't just plug in, you're not supposed to plug in a device and just have it suck massive amounts of power right away. That's really bad. So what the power switch does is you plug in the device, it only powers on the FTDI part until it properly enumerates with the PC, and it will say, give me more current, and then it enables the rest of the circuitry. It's just a nice, safe way to do it. For the adjustable target voltage, we're using PWM, pulse width modulation, from the propeller into an op-amp. So the duty cycle of the PWM is going to ultimately correspond to the output voltage, and we can do 0.1 volt increments. So we basically take our PWM, goes through a low-pass filter, through an RC filter, and then the op-amp is actually just a voltage follower to serve as a buffer. It has pretty good output current, so we can actually sort of use our target voltage output to maybe power a portion of a circuit or something like that. I wouldn't really recommend that, but you could do it. You get about 150 milliamps output. Level translation, I use some TXS 0108 bidirectional level translators. And again, that's just to let us convert the 3.3 volt signals from the prop over to 1.2 to 3.3, which is what I call VADJ, which is the adjustable target voltage. And you can actually set these to have like a high impedance state when they're not in use. So you can basically the I/O pins on the Jtagulator don't get enabled until you run the command. So everything's high impedance. You can connect stuff up to a target device without risking any damage before you're ready to actually start running stuff. And then the input protection. Since we have a target board, we don't necessarily know what test points we're actually connecting to, right? Like we might accidentally connect to like some portion of a power supply or some portion of like an LCD driver or something that's like a high voltage pin. We don't know. So we need to have some sort of input protection to protect us, to protect our hardware from getting damaged. And the way I do this is I have 1K resistors, and I have diode clamps going up, pulling up to one rail and down to ground. And the way the diode clamps work, if you look on the right side, we basically will be protected to the negative forward voltage of the diode and to the positive forward voltage plus VDD. So we basically just need to make sure that the diodes we choose protect the input lines, or the input pins of the propeller, and they're within spec of the propeller. And to do that, we needed something that had a really low forward voltage. So we ended up using some Schottky diodes, which are really fast and have low forward voltages. And we just have those on every single pin. Bill of materials. The unit costs about $50, $51 in single quantity if you want to build your own. So when you go on the Parallax site and say, well, why is it $160? Because the parts already cost a third of that. If you end up buying, you can't really get good quantity discounts until maybe you're up to like 1,000 or more, and we're not making 1,000 or more at a time. You can easily go buy your own on DigiKey and build it from scratch if you want. So a little bit on the firmware side, and I'll give you the demos. I have a bunch of different routines, basically like different modules. So the Parallax serial terminal is used for the debug interface of the user, the command interface of the user. Real random is a random number, pseudo-random number generator that I'm using to test we use for one of the commands to test the bypass state if we think we found a JTAG device, which I'll show you. Prop JTAG is all of the routines specific to JTAG. and then JTAG serial is what I'm using for the UART detection. So as you add more stuff, you can like grab another spin module from the Parallax Object Exchange or something, or write your own, and just kind of load it into the tree. Here's just a quick view of red, or the color on the left, means that's data that's used in the prop. Blue is unused. So there's lots of space left in there to do all sorts of super cool stuff. And if you guys do want to contribute to the project, I'm more than happy to help you out there. Okay, so how are we actually detecting JTAG? That's sort of an important thing. There's two different ways we're doing it. One is with the IDCODE Scan, and we're assuming, in this case, that each device in the chain will have the device ID enabled, which usually is a pretty safe assumption, even though it's an optional thing. If the device ID is enabled, it's going to be in the data register on reset, on device reset, or on reset of the tag. So what we do is for every possible permutation, we're going to set the reset, we're going to try to reset pins that we think might be the tap, right? Because we're trying every possible combination. So we send a reset. Then we basically move to the shift data register state, shift data out. If it ends up looking like a potential ID code, then we print that out and move on to the next one. ID codes always have to have their least significant bit high, so we can take advantage of that. If it's not high, then we know it's not correct. And the scope screenshot sort of shows you if red actually worked on the projector, you'd be able to see the data being shifted out on TDO, and that's the device ID. And in this case, we don't need to look for TDI, so you'll see that doing an IDCODE scan is a lot faster than doing a bypass scan, but then we don't know what pin TDI is. So eventually we're going to need to do a bypass scan anyway, but at least if you do an IDCODE scan first, it's faster. So here's a link to the JTAG report that issues the device IDs to different manufacturers. So once you get your device ID, you can start working backwards to figure out what it is. And that can also be used to help you validate that what you found is actually the right device ID. Bypass scan, we're forcing every single device on the chain into a bypass state. And since we don't know how many devices might be on the chain, we're just sending a lot of ones, a lot of data to force everything in. Because to enter bypass state in a chip, you have to send all ones for whatever the instruction register length is. But we also don't know what the instruction register length is, which could be anywhere from 2 to, 1,024, maybe even more. So we just send a shitload of ones to force every chip into bypass state, which has to be supported by the JTAG device. And then we send data in on TDI and count how many clock cycles it takes to get to the other side. And if we see something come out on the other side, then we know that we found the pins, and then we can count how many clock cycles and know how many devices there are in the chain. So it's sort of a cool thing. But it takes a lot longer because we're sending so much more data. And that's what's called blind interrogation, to actually see how many devices are in the chain. So moving on to the UART scan. For the UART scan, what we're doing is basically just sending data on TX. You have an option of sending a user-defined string or character on what you think is the TX pin. It will look for responses on the RX pin. So here's just a screenshot of sending data at different baud rates on the TX pin, and you'll see eventually, it's trying, we're decoding data but it doesn't look right, and then at the correct baud rate, we actually see a response back from the device that says $carriage return. So we're sending hello as the string. So we see that response, Jtagulator will print that out. We're doing everything at 8N1, 8 data bits, no stop bits, no parity, 1 stop bit. That's just a standard. Even if you don't have the parity and the data bits set up quite right, if you found the UART, you'll see responses back. And then if you want, you can go and try to figure out the other settings, which are just finite settings. Baud rates, there's a bunch of different standard baud rates that we're checking through table lookup. You can always add more if there's something that you think is non-standard, something or other that you might be trying to detect. So scan timing, I just put in here, basically, to give you an idea, if you only have 4 channels that you're looking at, it's only 24 permutations, you're basically going to get it right away. But if you're looking at 24 channels in a bypass state where you're looking for all 4 pins of JTAG, it's 255,000 permutations. You're just not going to do that manually, I hope. And that will end up taking about 5 hours at the max. So you do that, you go to lunch, take a really long lunch, have a drink, come back, and we'll be done. UART takes about 1 permutation a second, because we're doing 24 baud rates per permutation. So basically, you know, 4 channels, 8 channels, is 56 permutations. It's going to take a minute. All right, here's some demos. While I get stuff set up, I'm going to have a volunteer come up here to show some demos. Let's see, who's brave enough to raise their hand? Okay, she's not raising her hand, but I'm going to pick her anyway. All right, this is Leah, everybody. Say hi to Leah. Hi. Okay. So Leah's a friend of mine, but she has never used the Jtagulator before. I swear. For those of you that were at SummerCon, I called Space Rogue up and had him actually hook stuff up too. So she's going to go ahead and, oh, actually, no, not yet. I'm going to give one demo first of JTAG. She's going to hook stuff up for UART, so she'll just hang out for a second. I can't actually see what I'm doing. You know what? I need to share my screen. Sorry about that. You have any jokes to tell while I'm setting stuff up? Any Gouda? Any jokes about cheese or Gouda or anything? Yeah, okay. All right. There. Okay, so I'm going to... So right now the Jtagulator is set up. It's plugged in. Virtual COM port is showing up. I'm using CoolTerm. I'm going to open the connection. Hit enter. And here I'll reset the device. So you can actually see it comes up with a little header when I reset it. So 1.1.1. Hit H, you see the actual list of commands that are available. We'll do JTAG first. So I have a DEFCON 17 badge. I'm going to put the battery in it. This uses a Freescale MC56F8006. It just happens to have JTAG. So to have a safe demo, I wired up the JTAG pins to an actual connector, and I have a cable that I'm just going to plug in for this first demo. So I'm just plugging it in to save time. Okay. Now it's all plugged in, it's connected up to channels 0 through CH0 through CH3. I have to set the target voltage, 3.0. If I don't set the target voltage first and I try to do a command, it's going to give us an error. So let's see, we'll do the IDCODE Scan first, 4 channels, 24 permutations, Jtagulating, and right away it comes back, right? But we're not seeing TDI. So okay, we need to do the other one now. So now we know there's an interface. So do the bypass scan, 4 channels. 24 permutations again in this case. So here we go. Now TDI is 0, TDO 3, TCGate 1, TMS 2. That's our pin. So that's pretty cool, but let's verify that, right? Let's get the device ID. So now we can hit the D commands. What was that? TDO, was that 0? No, it wasn't. It was TDO was 3, 1, 2, 1 device in the chain. Yeah. Because we don't need TDI. TDI was the first one that returned. So now there's our device ID 01C0601D. That's the first one. You can go look that up. It's a Freescale device ID. Now what we can do is test bypass mode just to make sure. So 0, 3, you can hit enter if the pins are already the same. 0, 3, 1, 2, 1 device in the chain. So now we send our pseudo-random 32-bit string on the input and get 32 bits on the output. We do that. And you know, the data coming in is going to vary every time. Okay, so that's that. That's JTAG. I'm going to turn off the target voltage, and now I'm going to unplug this, and Leah is going to hook up a bunch of these wires arbitrarily, I don't care how she does it, into the pins. So CH0 to CH whatever, however many pins we have. So you can do that. I guess while she's doing that, let's see. I don't have any good jokes, I'm sorry guys. 20K. Oh yeah, okay. So this one. The wedding I just went to was so good, even the cake was in tears. I didn't write that one. I actually saw that one written in chalk on the sidewalk when I was out for a run one day. Alright, so she's almost done. Now the one thing to be aware of is you need to connect. There always has to be a ground connection, a shared voltage, shared 0-volt reference between the target board and the Jtagulator. So that's like the one piece of reverse engineering you'll need to do is find that shared ground. If you don't connect that, it's not going to work at all. Okay, let's make sure she didn't miss anything. Good. Nice. Okay, everything's connected. So we're going to set our target voltage. In this case, I think it's 3.3. And then our UART commands, identify UART pinout. We're going to just send the character return as our default string. And how many channels was it? 1, 2, 3, 4. 4 channels, 12 permutations. Now we wait. Not long enough to tell another joke though. So now we get lots of responses because we don't know the baud rate. And we can actually, convert that data to, or convert that string to different data at different baud rates. Most of it's meaningless though, so normally what I do is I'll start at the top and go, okay, go through the baud rates. Looks like TX is always 2 and RX is always 1, but try to find meaningful data. It'll print out the first 16 bytes that it receives back. Here's one that's 0D, right, carriage return I think, or line feed. But here's one that's 020A, so it's probably this one, 115.2K. So let's try that. Remember those settings. We're going to do the UART pass-through mode, which is going to allow us to actually pass through to the device that we're communicating with. TX is 2, RX is 1, baud rate 115.200. Now enter UART pass-through. Now we're actually at a login prompt for this Linksys WRT54G that's running DDWRT. So here we can actually mess with it a little bit, root, admin. And now we're in and we can start hacking stuff. We don't need any external level shifter or anything because now we're in and we can fuck with it and do whatever we want. So there you go. Everybody give up for the Yes.
Have you thought about putting something in that scans not standard baud rates for people to fuck up baud rates?
Have I thought about putting something in for non-standard baud rates? I did, and then I didn't put it in, so somebody can easily do that, or maybe I'll end up doing it. It's a table lookup, it's very easy. So once I'm done with the pass-through, I hit Control X, and now I'm back in the Jtagulator menu. So that's all in Jtagulator right now. Jump back to the presentation for a second. So there are some limitations. Every tool has limitations. This one does as well. If there's no interface, then you're obviously not going to be able to detect it. If there's a password, you're not going to be able to use it. Maybe there is, maybe there's some physical disconnection. So you might have to do more reverse engineering. Don't just email me and say it doesn't work, right? Because there's lots of reasons why it might not work. But when it does work, it's really, really cool. You can also actually abnormally fuzz. Since you're abnormally fuzzing pins, you might accidentally make the device into some other state, which isn't really a limitation. That might actually be pretty cool. Future work, again, adding support for other interfaces. If you want to get one, all the information is online. I've learned how to use GitHub just so I can put all the source code online. I'm really proud of myself for that. Everything's up there, schematic source code. Parallax sells assembled units, and I happen to have 10 of them left at a special DerbyCon rate. They have some online. They're handling all of that for me, so I don't have to, right? I can focus on development and hacking stuff and not have to deal with selling things and shipping things. You can also grab the bare board that I uploaded to OSH Park, which is a guy named Lane up in Portland who batches together different people's circuit boards onto giant panels to save money for everybody. It's a really cool hobbyist thing he's doing. So you can get bare boards from there as well. Parallax actually has bare boards as well, until they run out. Okay, final slide. I'm going to read a poem about the Jtagulator. I've been dying to do this. I paid a guy on the street in San Francisco $20. And I said, I'm working on this tool called the Jtagulator. He's like, what the fuck is the Jtagulator? I'm like, well, it's a cool hardware device. But he had no idea. But he wrote this poem, so here we go. To take an object from made to modified, customize interfaces between past and few truths can maintain their veneer in the face of signal feedbacks, size of diamond screwdriver, doesn't fit. Circuit, exit. Enter the dragnet on all sides, caught with tools, debugging, as form of how to gain access to what you have, but can't quite. Double-blind verify, ascertain, make salient discoveries about how electricity keeps its secrets from anything. That's not luckily everything. Electric is Jtagulator. Take apart a ball of something and find particles that can't be broken into. So there you go. Thank you. And if you guys want to ask questions, you just come up.